Hello, my dear future doctors, and a very, very warm welcome to you all. Cello, so today we're going to tackle a topic that is, I'm telling you, the absolute foundation for so much of your clinical life. We're going to talk about the body's amazing plumbing system, the blood vessels, and more importantly, what happens when things go wrong. You know, when there are leaks, traffic jams. And we'll also see the fantastic emergency repair system that keeps it all working. So let's dive right into hemodynamic disorders. But before all the heavy stuff, let me ask you a question. I'm sure you've felt this yourself. You get off a long bus or a train journey, and suddenly your chapals feel too tight. No? Your ankles feel all puffy. Or on a really hot day, your rings feel like they're trying to strangle your fingers. This isn't just some random feeling. It's a real physiological thing happening in your body, and it's our perfect entry point into our first big topic.
And that big topic is edema. That swelling, that puffiness we just talked about, that's it. Think of it as problem number one in our body's plumbing system. The pipes have started to leak. So let's figure out exactly how this happens and why. It's a beautiful concept, really.
Okay, for your Viva and your theory exams, you need this exact bookish definition, the accumulation of interstitial fluid within tissues. But let's simplify it for our understanding. It's basically waterlogging. The fluid that should be happily flowing inside your blood vessels has escaped and is now camping out in the surrounding tissues. Just picture a patient with heart failure, with those big swollen ankles. That's a classic and very serious example of edema. Now, to really get this concept, I want you to imagine something. Inside your tiniest blood vessels, the capillaries, there is a constant battle going on, right now. A fierce tug of war. And what are they fighting over? They're fighting over water. Each side is pulling, trying to control where the fluid goes. So, who are these fighters in this tug-of-war? On one side of the rope, you have hydrostatic pressure. He is the pusher. This is just the physical pressure of the blood, all thanks to your heart's pumping action, and its job is to push fluid out of the vessel. And on the other side, you have the puller. This is colloid osmotic pressure. It's like a suction force created by proteins in the blood, especially our hero albumin, and its job is to pull the fluid back in. Normally, these two forces are in a perfect, delicate balance. Edema happens when this balance is broken. Simple.
Bacha, this table is the absolute core of edema. Very, very important for your exams. So how can that balance be broken? Well, look at the first row. In congestive heart failure, the heart pump is weak, right? So blood backs up in the veins. This increases the pusher pressure, and fluid gets squeezed out into the tissues. You will see this on the wards every single day. Now look at the second one. In liver cirrhosis or severe malnutrition, the body just can't make enough albumin. So what happens? The polar force becomes weak, and again, fluid leaks out. So you see, it doesn't matter if the pusher gets too strong or the puller gets too weak, the result is the same: leaky pipes and edema.
All right, so we've seen what happens when fluid leaks out of the pipes. Now let's move on to the next plumbing problem. What happens when the pipes themselves get choked up? This brings us to the traffic jams of our circulatory system, hyperemia and congestion. Now you have to understand, not all traffic jams are created equal. Hyperemia is an active process. It's a planned diversion. Think about what happens when you exercise. Your body intentionally opens up the arteries to your muscles to let more oxygen-rich, bright red blood rush in. It's purposeful. Congestion, on the other hand, is a passive mess. It's a jam because the exit ramp is blocked. The veins can't drain the blood away, so deoxygenated bluish blood just gets stuck, backing up and causing problems.
And here is the classic result of that passive traffic jam in the liver. Look carefully, my dear students. This is a sight you will never forget. And I promise you, you will see this in your pathology practicals. This is the nutmeg liver. Why nutmeg? Because if you cut a nutmeg seed, it has this exact same mottled pattern of dark and light areas. The dark, reddish-brown spots are where the central veins are completely choked with backed-up blood. The lighter, tan areas are the liver cells that are, for now, relatively okay.
And now, under the microscope, we can see the tragedy behind that nutmeg pattern. We are looking right at the center of the lobule. It's filled with red blood cells, you can see hemorrhage, but look closely. The hepatocytes, the liver cells, they are dying. This is centrilobular necrosis. These are the cells that are furthest from the fresh oxygen supply, so when the traffic jam happens, they're the first ones to suffocate and die. This connection, from what you see with your naked eye to what's happening at the cellular level, that is the whole beauty of pathology.
Okay, so we've seen leaky pipes and blocked pipes. But what happens if a pipe actually breaks? You get a cut. What then?
Well, the body has an absolutely incredible, super fast emergency repair crew. And this life-saving process, my friends, is called hemostasis.
The textbook will tell you it's the process of forming blood clots at sites of injury. But that simple sentence hides a world of beautiful, beautiful complexity. This is not just about randomly plugging a hole. No, it's a perfectly controlled, step-by-step process. And thank God for it, because without hemostasis, even a tiny paper cut could be fatal.
Think of it like a perfectly practiced emergency drill. So, a vessel wall is injured. Step 1, in a fraction of a second, the vessel clamps down. That's arteriolar vasoconstriction. It's a reflex to immediately reduce blood flow. Step 2, the first responders arrive. These are our platelets. They rush to the scene and form a temporary plug. We call this primary hemostasis. Step 3, the heavy-duty construction team arrives. They lay down a protein mesh called fibrin. Think of it as cement to make the plug really strong. This is secondary hemostasis. And finally, the clot is stabilized and remodeled so the actual tissue repair can start.
So a very good question is, how do these platelet first responders know where to stop? How do they stick? It's brilliant, actually. When a vessel is injured, the stuff underneath the endothelial cells gets exposed. This includes a special protein called von Willebrand factor, or VWF. Just think of VWF as superglue that gets smeared all over the injury site. The platelets, in turn, have a specific receptor, a kind of handle, that is designed to grab onto this VWF glue, and that is how they stick firmly to the wall and start the whole process.
So, let's summarize what the platelets do in 3 key steps. First is adhesion, sticking to the wall, which we just saw. Once they stick, they get activated. They literally change their shape from a smooth disc to a spiky ball, and they start releasing chemical signals. These signals are like a cry for help, which leads to step 3, aggregation. More and more platelets hear the call and come rushing to the site, piling on top of each other to form that primary plug.
And now, we come to the part that gives students nightmares, the coagulation cascade. But please, forget those complicated charts for 1 minute. I want you to imagine something much more fun. Imagine a huge, grand Bollywood dance number. It's a perfectly choreographed sequence where one dancer activates the next, who then activates the next, all leading to a spectacular grand finale.
See, even your textbook agrees with me. It says the cascade can be likened to a dance. Each of these coagulation factors is just a dancer waiting backstage, inactive. When it's their turn, their partner on the dance floor activates them. They then do their step, and in turn, activate the next dancer in line. It's a beautiful cascading chain reaction.
So what is the whole point of this entire elaborate performance? All this dancing, all this activation, for what? It has one single, absolutely critical purpose: to convert a protein floating around in your blood called fibrinogen into an insoluble, tough, stringy fibrin mesh. This is the real cement. This is what makes the clot strong and properly seals the wound. Now, in your books, you'll read about 2 main choreographies for this dance, the extrinsic and intrinsic pathways. They can be very confusing. So to keep it simple, for what actually happens inside your body, just remember this. The extrinsic pathway provides the initial spark. An injury exposes something called tissue factor, and that kickstarts the whole dance. The intrinsic pathway then acts as a massive amplifier, boosting the reaction 100 times over to make sure enough fibrin gets made. And if this whole dance number was a Bollywood movie, then the undisputed superstar, the Shah Rukh Khan of this film, is thrombin. Just look at all the things it does. It performs the grand finale, converting fibrinogen to fibrin. It shouts at the platelets, "Come on, get more active!" It taps other dancers on the shoulder, factors 5, 8, and 11, to make the dance even bigger. And amazingly, it also helps to make sure the clot doesn't go out of control. What a performer, no?
So we've just seen this amazing, almost perfect system of clotting, this beautiful, complex dance. But so what? Why does it matter so much? It matters because when even one tiny step in this choreography goes wrong, the consequences for our patients can be absolutely devastating. This is where your textbook knowledge meets the real world at the bedside.
This slide shows you a very stark and clinically vital contrast. On the left side, you see petechia, tiny little pinpoint bleeds under the skin. This is what you see when there's a problem with primary hemostasis, like not having enough platelets. But look to the right. That is a massive, life-ending bleed inside the brain. This is the kind of catastrophe you can see with a defect in secondary hemostasis, like in hemophilia, where a clotting factor is missing. The type of bleeding tells you where the problem is. Is it the first responders, or is it the cement? This is how pathology guides your diagnosis.
And that brings us to our final question for today.
a really important one to think about. We have just admired this incredibly powerful, super fast, and efficient system for making clots. So, what stops it? Why doesn't a small cut on your finger trigger a chain reaction that turns your entire blood supply into one solid block of jelly? Well, the answer lies in another equally beautiful system of checks and balances. A system that keeps everything in equilibrium. And that balance, quite literally, is the difference between life and death. We'll explore that next time.
Hello, students, and welcome back. Today, we're going to trace a really dangerous journey inside the human body. We're going to follow the path of a blood clot, a journey that can start silently, but believe me, it can end in total catastrophe.
So, let's start with a question. A long flight, a heart attack, a really bad infection, what could they possibly have in common? They seem completely unrelated, right? But they all share a common, deadly potential.
Exactly. The link is that they can all kick off this deadly cascade that starts with thrombosis, the formation of a blood clot. So today we're going to understand this entire process, step by step.
We'll follow this story in 4 parts. We'll start with how the clot forms, then see what happens when it travels, the damage it does when it gets stuck, and finally, the ultimate devastating consequences for the whole body. Okay, Cello, let's dive into this.
So, first things first, let's meet the villain of our story, the thrombus. How does it even form? And maybe more importantly, why does it form? What are the conditions that allow this killer to be created right inside our own blood vessels?
Now, pay very close attention here. This is extremely important for your exams. Viva me, theory me, I guarantee you this will come up. You must remember Virchow's triad. These are the 3 main factors that create the perfect storm, the perfect conditions for a clot to form.
Okay, first, endothelial injury. Just think of the endothelium as this super smooth, non-stick coating inside all your blood vessels, like a Teflon pan. But when it gets damaged by things like high cholesterol, inflammation, or toxins from cigarette smoke, it becomes rough and sticky. And that is where all the trouble begins.
Now, what's really interesting is how abnormal blood flow contributes. Look at this picture. This is a massive aortic aneurysm. The blood flow here isn't smooth and straight. No, it's chaotic, it's turbulent, kind of like a whirlpool. This turbulence and slowing down of blood, stasis, it creates the perfect breeding ground for clot.
The third part of the triad, bachcho, is hypercoagulation. Matlab, the blood itself is just too clot happy. It's predisposed to clotting. This can be for primary, genetic reasons like the factor V Leiden mutation, or it can be secondary and acquired from situations like cancer or even just being on prolonged bed rest after a surgery.
And listen up, not all thrombi are created equal. Arterial thrombi, the ones causing heart attacks and strokes, they're rich in platelets and form in high-flow areas. Venous thrombi, on the other hand, the ones usually in the legs, are full of red cells, and they form where blood flow is slow, in stasis. This difference is absolutely critical for diagnosis and treatment. And this picture, this is a brilliant illustration of a mural thrombus. Mural just means wall, so this clot is actually forming on the wall of the heart itself. This often happens after a heart attack has damaged the muscle, creating an area that doesn't contract properly. It's a very, very dangerous situation.
So, once a thrombus is formed, what's its fate? What happens next? Well, it has 4 possible paths. It can propagate, meaning it gets bigger. It can dissolve, broken down by the body, or it can get organized into scar tissue. But the most dangerous path, of course, is embolization, when it breaks loose and travels. And that's where our story goes next.
Okay, abhi story mein twist aata hai. The thrombus, our stationary villain, now becomes an embolus, a rogue traveler moving through the bloodstream. The plot is definitely thickening.
So what exactly is an embolus? Well, think of it like a piece of debris floating down a river. It's just a detached mass, usually a piece of a clot, but not always, that travels with the blood until, inevitably, it gets stuck in a narrower vessel downstream.
This is the classic textbook journey of a pulmonary embolus. It's a very common and life-threatening event, and it almost always starts from a DVT, a deep vein thrombosis, way down in a leg vein.
Look at this specimen. Dekho isko. This is a massive saddle embolus. It's called that because it has straddled the bifurcation, the fork in the road of the main pulmonary artery, completely blocking blood flow to both lungs. This is a catastrophic medical emergency. It can cause sudden death in minutes.
But please remember this, students. It's not just blood clots that can embolize. Fat droplets after a big bone fracture, air bubbles getting in during surgery, and even amniotic fluid during childbirth can form emboli and cause devastating blockages in the circulation.
All right, so we've got this traveling embolus. What happens when it finally gets stuck and blocks a vessel? Well, the result is infarction. The tissue downstream is completely starved of blood.
So the crucial point to remember is this. Infarction simply means tissue death. The fancy term is ischemic necrosis. When that blood supply is cut off, the tissue is starved of oxygen and nutrients. It basically suffocates, and it dies.
Now, infarcts can look different depending on the organ where they happen. We classify them as either red or hemorrhagic, which you tend to see in tissues like the lung that have a dual blood supply, or white, anemic infarcts, which happen in solid organs like the heart or the kidney. And here you can see the difference so clearly. On the left, a bloody hemorrhagic red infarct in the spongy tissue of the lung. And on the right, you see a pale, wedge-shaped, anemic white infarct in the solid tissue of the spleen. The appearance itself tells you a story about the underlying organ's blood supply.
Finally, we reach the most critical stage of our story, when the damage is so widespread or the initial event is just so severe that the entire circulatory system can no longer supply the body's tissues with blood. We enter a state of shock.
See, shock is not a disease in itself. It is a life-threatening syndrome where the entire body is shutting down. You can think of it as the final common pathway for many severe conditions, from massive heart attacks to overwhelming infections.
We broadly classify shock into three main types based on what has gone wrong. Is it a pump problem? That's cardiogenic shock. Is it a fluid problem? Just not enough blood volume? That's hypovolemic shock. Or is it a pipes problem, where there's system-wide inflammation from an infection? That's septic shock. So this entire cascade that we've just discussed, thrombus, embolus, infarct, shock, it's all a failure of homeostasis, right? A failure of a perfectly balanced system. Understanding this path is the first step. The next step, for you as future doctors, is to learn how to intervene, how to step in when this delicate balance is broken. So choice ke baare mein. Think about that.
All right, bachcha log, let's get started. Chapter 4, Part 3. Today, we're diving into something really dramatic. We're talking about shock. And specifically, we're going to explore what happens when the body's own army, its own defense system, becomes the very enemy that's trying to kill it. So let's just start with this one big question, huh? What happens when the very thing that's supposed to protect you becomes the killer? This isn't some movie plot, you know? This is the central puzzle of septic shock. And today, we are going to solve it together. So let's jump into the first stage. I want you to imagine a small fire, okay? But suddenly, it just explodes, a firestorm that consumes the entire city. That's what sepsis is like. It all kicks off as this massive, completely out-of-control metabolic firestorm inside the body. Now, for your exams, for your viva, for your entire career, this definition is everything. Sepsis is a dysregulated host response. Say it with me. Dysregulated host response. It is not the infection itself that's the main problem. No, it's the body's crazy, over-the-top reaction to that infection that causes all the life-threatening damage. Someone okay? The body is trying to help, but its response is just too much. So what does this firestorm actually look like on the inside? Well, these things called pro-inflammatory cytokines, they're the messengers of inflammation. They go completely nuts. They cause hyperglycemia, which is high blood sugar. And this is terrible because it weakens our neutrophils, our main bacteria-fighting soldiers. The adrenal glands, they just get exhausted. And because all this chaos is messing up the circulation, the cells aren't getting enough oxygen, so they start producing lactic acid. This, my friends, is the beginning of a total metabolic meltdown. But our body's a fighter, yaar. It doesn't give up so easily. So now we enter what we call the non-progressive stage. This is where the body makes a heroic attempt to get things under control. You can think of it like a city in a crisis. It starts rerouting all the power and all the resources to the most important places. You know, the hospitals, the police stations, the command centers. So how does it do this? Simple. It hits the code red button. All the major systems come online. Your baroreceptors sense the blood pressure is dropping, so catecholamines, like adrenaline, get pumped out. The RAS system in your kidneys kicks in to hold on to every drop of water. It's an all-out sympathetic nervous system alert, and its one and only mission is to maintain blood pressure, no matter what. And here's the most critical part of the plan. the body makes a very, very smart but very tough choice. It decides, okay, I have to sacrifice the less important areas to save the VIPs. So blood is shunted, or you can say redirected, away from the skin, the gut, the kidneys, and it's all sent straight to the main command centers, the heart and the brain. Now, I want everyone to pay very close attention because this is a classic 5-star exam question. In most other types of shock, like say from major blood loss, the patient's skin is cool and clammy. Why? Because of that blood shunting we just talked about. But in early septic shock, all that inflammation causes vasodilation, which means the blood vessels are wide open, so the patient can actually have warm, flushed skin. And this is a trap. It can fool you. You might think, oh, perfusion is fine, but it's a very dangerous illusion. You have to remember this difference. So we move to the next stage. And this is where the story, well, it takes a very dark turn. If that main problem isn't fixed, the body's own defenses start to fail. They actually start to backfire. We are now entering the progressive stage. This is the tipping point. The main villain of this stage, the big boss, is tissue hypoxia. This is the central problem. The tissues, the cells that make up all your organs, they are literally starving for oxygen. And an oxygen-starved cell is a dying cell. This widespread hypoxia is what kicks off a catastrophic chain reaction. This slide shows the vicious cycle perfectly. Just look at it carefully. The tissue hypoxia leads to more and more lactic acidosis. This acid then makes the blood vessels lazy. They just stop listening to the body's signals. So what happens? Blood starts pooling in the tiny capillaries instead of returning to the heart. This pooling makes the cardiac output even worse, which then leads to, you guessed it, even more severe hypoxia. Do you see it? It's a downward spiral. Each step makes the next one worse, and the cycle just spins faster and faster downwards. It's an incredibly difficult cycle to break. And if that vicious cycle is not stopped, we reach the final tragic stage, the point of no return. And at this point, the damage is so widespread, so severe, that even if we could magically fix the patient's circulation, recovery is just not possible anymore. Just read this quote from the textbook. Let it sink in for a moment. Survival is not possible. It's so powerful, so final. At this point, cells are literally breaking apart, leaking all their toxic stuff everywhere. The damage is done. And this widespread cell death, of course, leads to multi-organ failure. The kidneys shut down. The lungs fill with fluid, a condition we call shock lung. The heart muscle itself becomes weak. The gut starts to die. This systemic collapse, this cascade of one failure after another, is what ultimately leads to the patient's death. So, okay, enough of the theory. Let's bring all of this back to the hospital, to the patient's bedside. What does this all mean for our patients? And more importantly, for you as future doctors? This table tells a very simple, very clear story. If a young, healthy person has hypovolemic shock, maybe from an accident, and we manage it well, their chance of survival is excellent, more than 90%. But look at septic shock, substantially poorer outcomes. And this is true even with the best care in the best hospitals. That's why we have to take this so seriously. And this is the hard truth, Yar. Sepsis is a stubborn, difficult clinical challenge. For years, scientists tried to make drugs that targeted just one inflammatory molecule, but those therapies all failed. Why? Because, as we've seen, sepsis isn't one simple thing. It's a complex, chaotic firestorm. You can't put out a forest fire with one bucket of water, can you? So I'll leave you with this one last thought, a question to take home with you. Now that you know this entire story, this whole cascade from the first little spark to the final irreversible organ failure, where is your golden hour? Where is the most critical window for a doctor, for you, to intervene and stop this runaway train? Think about it carefully, because finding that window, that's the difference between life and death. Okay, that's all for today. We'll continue this next time.